All right, we're going to finish up this chapter by taking a look at osmosis and dialysis. The human body is roughly 60% water, and the blood in our veins and the cytoplasm in our cells are aqueous solutions. So, how are the physiological concentrations of these solutions maintained? The answer is quite complex, but osmosis plays a critical role in this regulation. Osmosis is the means by which your cells take in water and some essential nutrients, as well as the method by which some wastes are removed on the cellular level. To help better understand this concept, consider the experiment that you see here shown in figure 6.31, in which pure water is separated from a sugar solution by a semi-permeable membrane. The membrane has pores large enough to allow small molecules like water to pass through, but small enough to prevent the passage of larger molecules like sugar or hydrated ions. Now, in this experiment, a semi-permeable membrane separates a sugar solution from pure water, which creates a concentration difference between the liquids. Water molecules move through the membrane in both directions, but the membrane prevents the diffusion of sugar molecules into the pure water to equalize the concentration. And as a result, the net flow of water through the membrane is into the sugar solution. This increases the volume of the sugar solution, which decreases its concentration to a value that's closer to that of pure water. The movement of water creates a difference in the liquid levels, a difference in height that you see here, which causes a hydrostatic pressure against the membrane. This pressure increases until it becomes high enough to balance the tendency for net water flow through the membrane into the sugar solution. From that time on, the flow of water in both directions through the membrane is equal, and the volume of liquid on each side of the membrane no longer changes. The pressure exerted by water that is required to prevent the flow The pressure exerted by water that is required to prevent the net flow of water through a semi-permeable membrane into a solution is called the osmotic pressure of the solution. The process in which the solvent molecules move through semi-permeable membranes is called osmosis. The same is true for solvent molecules other than water, meaning solvent molecules will also flow osmotically through semi-permeable membranes, separating solutions of different concentrations. The net flow of solvent is always from the more dilute solution into the more concentrated solution. You see that right here. The water is going from the more dilute solution, where it's pure water, into the more concentrated one, which has the sugar in it. A real-life example of osmosis affects the shape of red blood cells, as we see here in figure 6.32. A hypertonic blood plasma solution has a higher concentration of solutes than the interior of the blood cell. In a hypertonic solution, the osmotic pressure on the inside of the cell is greater than on the outside of the cell, resulting in an overall net flow of water out of the cell. When this happens, the blood cell shrinks and crenation or plasmolysis is observed. So the way to think about this is in a hypertonic solution, you have more solute particles outside of the red blood cells. And so water is going to come out of the red blood cells and to try to make the aqueous environment outside of the cells more like the environment inside the cells, and it's going to cause them to shrink or collapse, which is crenation. An isotonic blood plasma solution has the same concentration of solutes as the interior of the blood cell. In this case, the osmotic pressure on either side of the cell membrane is equal. As a result, water molecules diffuse into and out of the blood cell at the same rate. There is no net flow of water in either direction. And so the red blood cell is just going to maintain its normal shape. A hypotonic plasma solution has a lower solute concentration than the inside of the red blood cell. In this case, the osmotic pressure is greater outside the cell, causing an overall net flow of water into the cell. As a result, the red blood cell swells, or in extreme cases, undergoes hemolysis, which means it bursts. Let's take a look at example 6.12. It says the physiological concentration of sodium chloride in cells is around 0.1% weight over volume. Using your knowledge of osmotic pressure and the shapes of cells, determine whether a cell will undergo crenation or hemolysis will exhibit no change in volume in a solution of 0.5% weight over volume. So if it's in a solution that's 0.5% weight over volume, that means there's a greater concentration of solute particles outside of the cell than there are inside of the cell. Okay, and so if I label this as my cell, what's going to happen is that the water is going to come out of the cell like this to try to bring the concentration of particles outside of the cell to be lower, to be more like that concentration that's inside of the cell. And so if the water is coming out, it's going to shrink or undergo hemolysis. Dialyzing membranes are semipermeable membranes with larger pores than the osmotic membranes that we've talked about so far. They hold back large molecules but allow solvent, hydrated ions, and small molecules to pass through. Recall that the net flow of particles down their concentration gradient, meaning from high solute concentration to low solute concentration, is called diffusion. The diffusion of these ions and small molecules through such membranes is called dialysis. An application of dialysis is called hemodialysis, which is used to remove waste particles from the blood of people with failing kidneys. Hemodialysis takes advantage of the fact that dialysis can be used to separate particles from large molecules. The blood from a patient undergoing hemodialysis contains medium molecular weight particles, such as proteins, that must be retained, and low molecular weight impurities, such as urea, that must be removed. As the patient's blood enters the dialysis chamber, an aqueous solution with essential biological ions enters it too. The purpose of the aqueous solution is to maintain the biological ion concentration while also carrying away the low molecular weight impurities. The impurities pass through the membrane down their concentration gradient and out of the chamber. Water molecules move through the membrane in both directions, but the medium molecular weight particles, like blood proteins, remain inside the chamber and are returned to the patient's bloodstream. And so we finished this chapter, and so you should be able to calculate the kinetic energy of moving particles, of course, using the formula that we talked about. You should be able to convert pressure and temperature values into various units. You should be able to do calculations based on Boyle's law, which relates pressure and volume, Charles' law, which relates volume and temperature, and the combined gas law, which is P pressure times volume over temperature. So it's a combination of Boyle's law and Charles' law. You should be able to do calculations based on the ideal gas law, which is PV is equal to nRT. You should be able to do calculations based on Dalton's law of partial pressures, which is P total is equal to P1 plus P2 plus P3, etc. Apply your knowledge of intermolecular forces to determine the solubility of substances in a given solvent. So you should know ion dipole, dipole dipole, hydrogen bonding, and London forces. You should be able to write molecular equations in total ionic and net ionic equation forms. Calculate solution concentration. So you should know molarity, percent weight over volume, and percent volume over volume. Describe how to prepare solutions using the dilution formula. M1 V1 is equal to M2 V2. Describe what osmosis is and describe the role of osmosis in diffusion in dialysis.